Hi, so for today we're going to talk about Cartesian vectors, and for today's video we're going to discuss some of the important formulas in solving resolution of forces along x, y, and z axis, and we're going also to talk about the Cartesian vectors, of course direction, cosines, magnitude of these vectors. Okay, so let's get started. So Cartesian vector, a vector A such as this vector may have one, two, or three rectangular components along the x-axis. This is our x-axis, and this is our y-axis, and this is our z-axis. Now we are entering the three coordinate system, which is x, y, and z axis. And basically, if we're going to project vector A into its components along the x, along the y, and along the z, we'll be having this notation. We have the A is equals to AX plus AY plus AZ. So, Cartesian unit vectors. In three dimensions, the set of Cartesian unit vectors I, J, K is used. Okay, to denote that they are in the direction of I for X, J for Y, K for Z, respectively. Okay, so this unit vectors, Cartesian unit vectors, is a vector that has a magnitude of 1. So it's very useful to use in our calculation of components, okay, when we are using this unit vectors. So, as you can see, if we are going to include the unit vectors I, J, K, will be having this formula, okay, as the vector A is equal to AX, that's the component of vector along X, multiplied by the unit vector I hat, or I, simply in terms of boldface font, okay, so plus A sub Y, J plus A sub Y, A sub Z, K. So we can see here that we have an AX in the I direction, meaning with the X axis, we have A sub Y in the J direction, okay, along Y axis, and we have A sub Z, K along the Z axis. So, this is the magnitude and this is the direction, okay, the unit vector. So, separating the magnitude and direction of each component vector will simplify the operations of vector algebra. Usually, if we are to express the vector in this form, vector algebra is really easy. Unlike if it is not expressed in terms of components. Okay? So, we'll be using this would be very handy in three dimensions. So, what is the magnitude of a vector? Again, the magnitude of a vector is basically the length of the vector. Okay? So, the magnitude of a vector is always results to a scalar, and that is equivalent to this formula. The magnitude of the vector A is equal to the positive square root of the sum of the square of its components. A sub x, A sub y, A sub z are components. A while ago, these are components. Okay? And I, J, K are their direction to indicate that this is a vector. But in getting the magnitude, we simply square the components. Get the summation of the square of the components, okay? And take the square root of it. That is the magnitude of a Cartesian vector in 3D, okay? So such that if we have a vector A here, of course, in two dimension, we label only the direction of a vector in terms of theta. But in these three-dimensional coordinates, we have what we call the direction of a Cartesian vector, which is called the direction cosines. Okay? We can express the direction of this vector A with respect to each axis, x, y, and z. So, for example, we have a vector A here. And this vector A, if we are going to measure the angle of vector A with respect to the x-axis, which is this, okay, that is what we call the alpha, that angle alpha. And of course, if we are going to measure the angle of vector A, okay, from the y-axis here, we have the beta, this angle beta, and for the z, we have the gamma, which is this Greek alphabet here. Okay, and in order for us to get that direction cosines or direction of vector with respect to the respective axis of the 3D coordinates, we have to get, well, of course, the inverse cosine of alpha ax over a. So where did this formula come from? It's basically, it comes from this, okay, image. Wherein if we're going to project this vector a, okay, onto the x-axis, we'll be having this. This would be our ax, okay? Ax, this would be our ax, okay? Because we projected this a into our ax. And this is a 90-degree angle, so that if we're going to get the cosine of this alpha, okay, the cosine of this alpha, we'll be getting ax over a, okay? And of course, if we resolve this vector a into our y-axis, this is a sub y, okay, we'll be having that beta, and if we get the cosine of this beta, okay, that is cosine adjacent over hypotenuse, which is a. So, ay over a. And lastly, for our gamma, this is our vector. If we resolve this into z-axis, we have this a sub z, and this is still 90 degrees, such that if we're going to get the cosine of this gamma, that is az over a. Hence, we have this formula. Okay, in order for us to get the real value or the degree, we are going to get the arc cosine of each of this angle. Okay, so these are what we call the direction cosines, and it is very important to know this, familiarize ourselves with the formula. Okay, so unit vectors, as what I have said a while ago, unit vectors are vectors that has a magnitude of 1. There is an if we are going to get direction cosines of a certain vector, it is very important, or what would I say? It's very much more easier to get the direction cosines of a certain vector if we are going to get what we call the unit vector of that vector A in its direction. So the unit vector is denoted by U sub A. Unit vector, this means unit vector in the direction of vector A. And that is simply the vector A multiplied by the magnitude of A. So vector divided by a scalar, it would be a result of a vector quantity. And as you can see here, each of the components is divided by its magnitude. So ax over a, ay over a, az over a. Okay, so we have I, j, k directions here. So because that is a unit vector. So this ax over a, as you can see, this is simply the cosine of alpha. Okay, as you can see here a while ago. So unit vectors, ax over a, if you know this, ax over a, then definitely you can get the direction cosine alpha with respect to x-axis, and so on and so forth. So it's very important to express, if you're going to get the direction cosines or the direction of this vector along x, y, and z axis, okay, you must first express the given vector in terms of its unit vector for you to be easily to compute the direction cosines. Okay, so that is the unit vector. The vector itself divided by its magnitude. Okay, so the other formula for unit vector, as what I have said a while ago, cosine alpha is equal to ax over a. So this ax over a is replaced now by cosine alpha. And of course, this is ay over a, cosine beta. And of course, this is a sub z over a. Okay, that is the cosine gamma. Okay, that's the unit vector. And from this equation, we can derive a very important relationship of which cosine squared alpha plus cosine squared beta plus cosine squared gamma is simply equal to 1. Okay, that is simply equal to 1. So, this is very important. This equation is very important because if we are given the cosine beta, cosine gamma, okay, if we are given two angles, for example, we are given the two direction cosines, the beta and the gamma, we can always get the alpha. And on the other hand, if we are given alpha and gamma, we can always get beta. And lastly, if we are given alpha and beta, we can get the gamma. Okay? So by simply using this formula. Okay? So sometimes the direction of vector A can be specified using the two angles. We have the phi, okay, and we have the theta. So let us realize that this figure we have vector A. Okay, if we are going to resolve it to our vectors, to the z axis, this would be the vector a sub z with a certain angle phi, and we call this, okay, we call this also the vector a prime. As we can see, this is a prime. Okay, this is equal to this. So, sometimes if you're going to get the components, it is very useful to use this. Why? Because, as you can see, we have a sub z here. If we are going to get a sub z here, this is phi, this is a prime. Let's label this as a prime. If you're going to get a sub z, simply cosine of phi is cosine, okay? Cosine of phi, remember that this is the right triangle. So, this is the hypotenuse. So if we get the cosine phi here, cosine phi is adjacent a sub z over the hypotenuse, which is a. Cosine phi is a sub z over a, such that if we're going to rearrange that, this would be our equation where we can get the a sub z. And on the other hand, if you're going to get sine phi, okay, sine phi, remember this is a prime, sine phi opposite a prime over hypotenuse over a, such that this would be our formula. Why do we need to get a prime? Because a prime is the same as this. In getting the a prime, we can get the x and y component. In getting the x and y component, we have to know what is the magnitude of a prime so that we can resolve that a prime, or simply this a, into x and y axis. So that if we know the a prime, this a prime is the same as this a prime, so that it can be moved. Okay, so this would now be our a prime, this is our theta, and if we are going to get, this is equivalent also to a sub y. Okay, a sub y, this is a sub x, so that if you're going to get cosine and sine of theta, we'll be having this formula: ax, a prime cosine theta, of which a prime is a sine phi cosine theta. And of course, for a sub y, if we are going to get a sub y, we have to use a prime sine theta. And overall, this vector a can be rewritten as this from the given equation that we have derived. But take note, do not memorize this, because this equation is not always true. It is always true in this type of vector. What if the vector is in here? What if the vector is on the other side? So don't memorize. This is only purely based on the trigonometrical view, or trigonometry, based on the trigonometry. This is actually derived for the using trigonometric functions. Okay, so it's very important. So let's try to solve some problems. I have a problems here. Okay. Okay. So for problem number 1, okay, express the force shown as a Cartesian vector. Okay? So as you can see here, we have a problem here wherein we will express this force 200 Newton in terms of Cartesian vector. Cartesian vectors are in terms of ijk. So this is 200 Newtons. And it says here that we have an angle 45 and 60 degrees. So what is this angle 45 degrees? 45 degrees is the angle from the force F to the z-axis. So what is that? So that 45 degrees is the angle from this vector to the z-axis. That is labeled as our gamma. Of course, that is our gamma. And as you can see, the 60 degrees here is the angle between the vector to the y-axis, and that is our beta. And here, we don't know the alpha. Okay? That is the angle from the force to the x-axis, positive x-axis. So, what do we do now? So, it's very important for us, again, okay, to know what is this angle in order for us to write the Cartesian vector. And from our formula a while ago, as I have said, okay, if we know the two angles, beta and gamma, we can get alpha by this formula. by this relationship. Okay, is equals to 1. So that if we are going to solve this problem, so what are we going to do? Cosine squared alpha plus, okay, cosine squared of beta, which is 60 degrees, plus cosine squared of gamma, which is 45 degrees, is equals to 1. So if we're going to evaluate this should be cosine squared 60. Cosine squared 60 is 0.25. Cosine squared of 45, that is 0.5, is equals to 1. If I'm going to get cosine of alpha here, okay, that is equivalent to square root of 1 minus 0.25 minus 0.5. And furthermore, if I'm going to get alpha, that is arc cosine of the square root 1 minus 0.25 minus 0.5. And our result, of course, okay, let's take note that we have two results here. So as you can see, we have this formula, okay? So we have, when evaluating the square root, we have positive and negative. So we have 1 minus 0.25 minus 0.5 would be the arc cosine of uh, positive or negative 0.5. Again, we have positive and negative because we're evaluating the square root. So we have two alphas. We have arc cosine of positive 0.5, and we have the second alpha, which is arc cosine of negative 0.5. And this would give us different values. So we have alpha 1, which is 60 degrees, and for alpha 2, if we evaluate that, alpha 2 is 120 degrees. Now, so as you can see, we have two answers here of alpha. So which one alpha is correct? Okay, so by inspection, this force F, okay, if we resolve this into f of x, this force is a positive f of x, should be in the direction of positive f of x. And if it is in the direction of the positive f of x, then its angle should be less than 90 degrees. So our alpha here by inspection is 60 degrees. So we have gotten our alpha, which is 60 degrees. So what is the point? The point is we can now get the Cartesian vector of this f by, of course, we have the formula cosine, okay, f cosine, okay, this is the magnitude, this is the vector, okay, this is the magnitude of the vector, f cosine alpha I plus f cosine beta j plus f cosine gamma k. Okay, that is the Cartesian vector, and our magnitude for our force is 200 cosine 60 I plus 200 cosine, what is our beta? Beta is 60 also, okay, plus, okay, 200 cosine of 45, okay, 45 degrees K. This is J. So if we are going to evaluate 200 cosine 60, that is 100 I. 200 cosine 60, that is 100 J. 200 cosine 45 is 141.4 K. Of course, this is our Cartesian vector in terms of Newton. How do we check? If we get the magnitude of our vector f, okay, our vector f, that should be equal to 200. 100 squared plus 100 squared plus 141.4 squared, that should equal to 200 Newton. So hence, our answer here, that is this Cartesian vector of this force, is correct. This is our final answer. Okay, moving on our second problem. Our second problem is determine the magnitude and the coordinate direction angles of the resultant force acting on this ring. Okay? As we can see here, our forces are now expressed into Cartesian vectors, Cartesian coordinates, okay? Or Cartesian vectors in terms of components. So, Fr is simply, the resultant force is simply F1, okay? We're going to perform algebra F1 plus F2 here. Okay? And Fr is simply what? We have 50I minus 100J plus 100K plus we have 60J plus 80K. Okay? Pounds. So we can add those with the same vectors. Okay? Unit vectors. We have 50. Okay? We have no 50. We have no I hat for the second vector, plus we have negative 100 plus 60J, and lastly we have plus 100 plus 80K. We have pounds here. So our answer should be 50I minus 40J, okay, plus 180K pounds. That is our resultant. So, as you can see, if that is in terms of Cartesian vector, it's very easy to get the resultant because you need not to get any angle and perform the component method in order for you to get the resultant. So, this is our resultant force in terms of Cartesian vector form. Okay? And if we are going to get the magnitude of the resultant, magnitude of Fr, okay, is simply 50 squared plus negative 40 squared plus 180 squared. And if we're going to get that, that is 191.0 pounds. Okay? So in other words, 191 pounds is the resultant force. Okay? Magnitude of the resultant force. And again, how about the direction angles of the resultant force? Direction angles, okay, in order for us to get the direction angles, the direction cosines of the resultant force, we need first to get the unit vector of the resultant force. The unit vector again is the this vector, okay, this vector, resultant force vector. Okay, this is a vector divided by the magnitude of the resultant force. And as you can see, our resultant force is 50I minus 40J plus 180K over the resultant or the magnitude of the resultant force. Okay, that's the magnitude. That is 191 pounds. So as you can see here, we have 50 over 191. Okay, I minus 40 over 191 J plus 180 over 191 K. And of course, as what we have studied, this is AX over A. Okay? In our formula a while ago, AX over A, AY over A, AZ over A. So, we can get now the direction cosines by, we have the formula cosine alpha is AX over A while ago. But this is in terms of FR. So that is still F, okay? We have the FRX over our magnitude FR. Okay? So what will happen? We have what? 50 over 191. That is for our alpha. Cosine alpha is 50 over 191. And if we're going to get the alpha, that is our cosine 50 over 191. And that is equivalent to 74.8 degrees. That is for alpha. And again, the alpha is the angle of the resultant force, okay, with respect to our x-axis. We have cosine beta, and our cosine beta is negative 40 over 191. Okay? We get beta here, arc cosine of negative 40 over 191, and that is simply equal to 102 degrees. Lastly, for our gamma, so we have 180 over 191. Okay? Gamma would now be arc cosine of 180 over 191 is equivalent now to 19.6 degrees. So, we have solved the problem. These are the direction cosines or the direction of the resultant force, direction angles, and this is the magnitude of the resultant force. So, you can see much easier if the forces are actually expressed in terms of Cartesian vectors. So this is our direction angles. So now let's proceed with our problem number 3. So we're going to express the force F shown in the figure as a Cartesian vector. Okay, as you can see, this is a typical problem wherein we can express this F again into Cartesian vector. But in this problem, you can see that we have an angle 60 degrees with this vector in here. That is, we have two angles. We have phi and theta. Okay? So that, okay, if we're going to resolve this force into its z-axis, okay, this would be our f of z. And that is the same f of z as here. Correct? Yeah, that is correct. Okay. And, of course, this is also a vector. Okay? We can label this from our discussion a while ago. This is our f prime. And this is the same f prime. Okay? That is the same f prime. So that, if I'm going to get the cosine function of that 60 degrees, cosine of 60 degrees is, this is our right angle. This is our hypotenuse. This is our f. Okay? This is our f. If I'm going to get cosine 60 degrees, that is adjacent, okay? Adjacent over hypotenuse. I can get f prime by f cosine 60 degrees. And if I'm going to get the sine function 60 degrees, what will happen? Opposite f sub z over opposite, this is the opposite of 60 degrees over, okay, hypotenuse, which is f. So in other words, I can get f sub z, f sine 60 degrees. So f prime would now be 100 cosine 60, and the result of that 100 cosine 60 is 50 pounds. How about f of z? F of z would be 100 sine 60 degrees. The result of that is 86.6 pounds. Okay, so f of z, we have already got it because, again, if we're going to recall, we can express this vector f in the Cartesian as the following. We have f of x, okay, I, plus f of y, j, plus f of z, k. Okay? We already have the f of z here. Of course, if this is f of prime, okay, and we're going to resolve this f of prime in terms of x, okay, terms of x, this, and in terms of y, this f of prime. So what will happen? We can get from our formula a while ago, okay, that f of x is equal to f of prime cosine of theta, and f of y is now f prime sine theta. So what will happen? We have f prime, which is 50 cosine, that theta is the 45 in here. Okay? Because if you're going to recall, this is our fy here. I'm sorry, this is the fy, and this is our f of x. Okay? If this f prime is resolved into x and y component. Okay? So this is our fx, this is our Fy in this direction. Okay? So, F prime cosine of 45. This is 50 cosine of 45 degrees. So, what will happen here? If we are going to have 50 cosine 45, that is 35 point, okay, 35.4 pounds, let's say 35.4 pounds, and 50 sine 45 is equivalent to the same 35.4 pounds. But take note, if I'm going to redraw this F prime, okay, F prime is in this direction, okay. This is our y-axis. I'm sorry, let me just redraw it. Okay. So this is our y-axis. This is our x-axis, as this is our f prime. Okay. So if we're going to resolve this, this is our y, this is our x. Okay. Negative x, this is positive x. I'm going to resolve this in terms of y. This is would be the f of y. In terms of x, this would be f of x. Okay? I transferred this vector to this such that the f of y becomes this. So that we have, again, this figure. Okay, notice that we have gotten a value of f of y that is a positive. Whereas, if we're going to resolve this f prime into the y-axis, that is going to the negative y-axis. So, this fy should now be negative. Okay? So, we have now the f of x, f sub x, f sub y, and f sub z. Therefore, the Cartesian vector form of this force is now 35.4i minus 35.4j plus 86.6 k. That is the Cartesian vector form of our force F100 pounds. So, if we're going to solve for the magnitude of this, square root of 35.4 squared plus 35.4 squared plus 86.6 squared, we'll be getting 100 pounds because that is the magnitude of the force. And what if we are also asked for the direction angles of F? Okay? So what will happen is that the direction angles of F, in order for us to get that, we have to get the unit vector of the F. And that is equivalent to the vector F, okay, in Cartesian vector form divided by the magnitude of the F. So we have, okay, let's first get the magnitude of the F. Okay? And the magnitude of the F is simply 100. Okay? To prove you that our answer is correct, we can get the magnitude. Okay? Negative 35.4 squared plus 86.6 squared. That is equivalent to 100. So we have 35.4 over 100 I minus 35.4 over 100 J plus 86.6 over 100 K. And if we're going to get the direction cosines, cosine alpha is equal to this 35.4 over 100, and that is alpha arc cosine of 35.4 over 100. The result would be 69.3 degrees. Cosine beta is now equal to negative 35.4 over 100. If we solve for beta, that is arc cosine of negative 35.4 over 100. And that is equivalent now to 111 degrees. Okay? Lastly, for cosine gamma, that is equivalent to 86.6 over 100. And our angle gamma is arc cosine 86.6 over 100. And that is equivalent to 30 degrees. And this should be our direction angles for our force, F. Okay? So, down to our last problem for this video. So, we have this given. So two forces act on the hook. We have F1, F2. This is specify the magnitude of F2 and its coordinate direction angle so that the resultant force F sub r acts along the positive y-axis. Positive y-axis, that is our resultant. So this should be our Fr according to the problem, and it has a magnitude of 800 newtons, right? So how do we solve this? So we are actually looking for F2 and its direction angles. Okay? So how do we do this? We will use the available facts that we can gather in as much as 4 to solve the F2. So we have F1 here. As you can see, this F1 has an angle, 3 angles. So F1 with respect to X, that is our alpha. Okay, F1 with respect to Y, that is our beta, and this is our gamma because it's for Z. So we can write the F1 as, again, okay, the vector, this is vector F sub 1, in terms of its Cartesian vector form because we all know the alpha, beta, and gamma. So we can rewrite this as the magnitude of F1 cosine alpha I plus the magnitude of F1 cosine beta, or plus F1 cosine gamma K. So if we do that, the magnitude is 300 cosine alpha, which is 45 I, plus 300 cosine beta 60 J, plus 300 cosine of 120K. If we evaluate this 300 cosine 45, that is 212.1 I. 300 cosine 60 is 150 J. Okay, 300 cosine 120 is negative 150 K. And this is in terms of the vector, Cartesian vector form of F1 in terms of newtons. Okay, how about the F2? The F2, we don't know. Okay, that is the unknown. But as you can see here, the vector F2, okay, has Y, has Z, and has X components. So we can rewrite this F2. This is the vector F2. Okay, vector F2 as simply F2x, okay, F2 in terms of xi plus F2yj plus F2z in terms of z direction. We have k. Okay, so we don't know. That is our k in terms of, again, in terms of Newton. Okay, but the resultant, we know. The resultant, it says 800 newtons. Okay, this is the magnitude. Okay, magnitude. And it's, if we're going to write Fr with magnitude and direction, it says along the positive y-axis. So it's a vector, the vector Fr, okay, if that is along the positive y-axis, that is 800J. Okay? So, now, we want to get F2. So that we have the following relationship. Fr is equals to F1 plus F2. Simply, because we are in the Cartesian vector form. So that is 800J is equal to, okay, we have 212.1I plus 150J minus 150K plus F2xi plus F2yj plus F sub 2zk. Okay? So, if we regroup like terms, so we have 800J here, and we have 212.1 plus the magnitude of force 2 in terms of x, F2x, factor out I, plus we have 150, okay, in terms of j, plus F2y, j here, plus, we have negative 150, that is our k, plus F2z, the component along z of the force 2, k. And by inspection, we have I, j, k here. and we have j only on the other side. By inspection, we can solve what? Are there any terms of I in this side of the equation? So, for solving f2x, we have 0 is equals to 212.1 plus f2x. Okay, there are no any I in this equation. So, this should be equivalent to 0. Okay, solving for f2x, we have f2x negative 212.1. Okay, of course, the unit of that is Newton. Okay, for J, we have 800J because we have 800 here on the right side. Okay, or of course, that is not 800J, 800 only because we are only computing for the components. We have 150 plus F2Y. So that if we're going to get F2Y, that is simply F2Y is 800 minus 150, and that is equivalent to 650 Newton. So 650 Newton. So this is our first answer, F2x 212.1, 650 for F2y. How about for F2z? As you can see here, equating this on the other side, we have 0 because we don't have any k vector here. So we have negative 150 plus F2z. So what will happen? F2z is simply 150 Newton. Okay, we have now we can write now our, okay, vector F2 in terms of Cartesian vector form, and that is negative 212.1 I plus 650J plus 150K, and that is our answer for Cartesian vector form of F2. But it says specify the magnitude of F2. So that is not still, I'm sorry, the answer is to get the magnitude of vector F2. So we have to get the negative 212.1 squared plus 650 squared plus 150 squared. And upon getting that, the magnitude is 700 newtons. And this should be our answer. And another question is we're going to get the direction angles. Get the direction angles of this f sub 2. And of course, in order for us to get the direction angle, we must first get the unit vector of f sub 2. Okay? And that is the vector f sub 2 over the magnitude of f sub 2. So we have negative 212.1 over 700 I plus 650 over 700 J plus 150 over 700 K. And that is our unit vector. And again, cosine alpha is simply equal to this. Negative 212.1 over 700. And if we solve alpha, that is 108 degrees. Okay? Alpha. We solve for beta, we have 650 over 700. Solving for beta, we have 21.8 degrees. I've done the shortcut. I've shown you a while ago on how to solve this. Simply, we have to get the arc cosine of this. So we have cosine gamma 150 over 700. And our gamma now would be 77.6 degrees. And that's it. That is our answer. The magnitude of force 2 is 700 newtons. And our direction cosines are the 108 degrees, 21.8 degrees, 77.6 degrees. And I hope you learned something from this video. Thank you so much. And don't forget to subscribe my channel and share it with other engineering students, particularly who are taking statics. So I hope you learned. Thank you so much for listening and God bless you.